You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your IT fundamentals certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. In this episode, we're expanding our understanding of core internal components by exploring three critical areas of modern computing systems: graphics cards, firmware interfaces such as BIOS and UEFI, and storage controllers. These parts go beyond the CPU and RAM to manage visuals, hardware initialization, and how data flows between the processor and drives. Whether you're configuring a custom desktop, troubleshooting boot issues, or analyzing performance, familiarity with these components is essential for IT support. This topic appears in Domain 2 of the ITF Plus exam under Internal Components. You may encounter questions that ask you to identify the function of a GPU, configure a BIOS setting, or choose the correct storage interface for a device upgrade. Some questions will present scenarios where a technician must solve hardware detection problems or recommend solutions based on firmware or controller behavior. Mastering these subjects strengthens your ability to diagnose issues and explain system functions to users and coworkers. Let's begin with the graphics card, also known as the GPU or Graphics Processing Unit. This is the component responsible for generating and outputting visual content to a monitor or display. While CPUs can perform basic visual tasks using integrated graphics, a dedicated GPU offers superior performance, especially for demanding applications like gaming, video editing, or 3D modeling. GPUs are engineered to handle many calculations in parallel, making them ideal for graphics and increasingly useful for artificial intelligence and scientific computation. There are two main types of graphics solutions: integrated and dedicated. Integrated graphics are built directly into the CPU or motherboard chipset. They share system memory and are sufficient for most general computing tasks, like browsing the web, running office applications, and watching videos. Dedicated graphics cards are standalone components installed into expansion slots. They have their own onboard memory and processing power, allowing them to handle high-resolution displays, advanced rendering, and graphic-intensive workloads without taxing the CPU. Installing a dedicated GPU involves placing the card into a PCI Express or PCIe expansion slot on the motherboard. Most modern GPUs require a 16-lane PCIe X16 slot for optimal performance. In addition to installation, the graphics card often requires one or more power connectors from the system's power supply. Output ports on the card may include HDMI, DisplayPort, DVI, or older connectors depending on the model. After physical installation, the system needs the appropriate driver software to fully utilize the card's features. GPUs are used for more than just gaming. In business settings, they enable video conferencing, drive multiple monitors, and support CAD software for engineering. In creative industries, they handle video rendering and real-time effects in applications like Adobe Premiere and Blender. In scientific research and machine learning, specialized GPUs accelerate calculations that would take traditional CPUs much longer. Even in general-purpose systems, GPUs play a vital role in delivering a smooth and responsive user interface. Next, let's look at BIOS and UEFI firmware. These are low-level software environments stored on the motherboard in ROM or flash memory. They are responsible for performing the post or power-on self-test when the system is powered on. During this stage, the firmware checks the CPU, memory, and storage devices for basic functionality before passing control to the operating system. Without working firmware, the system cannot boot. BIOS, or Basic Input/Output System, is the traditional firmware interface. It uses a text-based interface navigated with a keyboard and is limited in the size and type of drives it supports. UEFI, or Unified Extensible Firmware Interface, is its modern replacement. UEFI supports large storage devices, fast boot features, mouse input, and graphical menus. It also allows for secure booting, which helps protect systems from malware during startup. Most modern systems use UEFI, though the terms BIOS and UEFI are often used interchangeably. Accessing BIOS or UEFI requires pressing a specific key during system startup, often Delete, F2, or ESC. Inside the firmware menu, users can change boot order, enable or disable hardware components, configure CPU features, and set security options like BIOS passwords. Changes made in BIOS or UEFI are saved in non-volatile memory, meaning they persist after reboot. Misconfiguring these settings can cause boot failures or other system instability, so changes should be made carefully and with documentation. Firmware updates are sometimes needed to add support for new CPUs, improve compatibility, or fix bugs. These updates are released by motherboard manufacturers and must be applied using their specific procedures. Updating BIOS or UEFI carries some risk. If power is lost during the process, the motherboard may become unbootable. Therefore, updates should be done only when necessary, such as when upgrading to new hardware or addressing a documented issue, and should always follow vendor instructions. Now let's explore storage controllers. A storage controller is a hardware or firmware component that manages communication between the CPU and connected storage devices like hard drives and solid-state drives. These controllers determine how data is read from or written to storage media. Most are integrated into the motherboard, but some systems, especially servers, use add-in controller cards for advanced storage configurations. There are several types of storage interfaces supported by controllers. SATA, or Serial ATA, is a common interface for both hard drives and SATA-based SSDs. It offers reliable performance for most applications and is widely supported. NVMe, or Non-Volatile Memory Express, is a newer interface designed for SSDs that connect via PCIe. It offers much higher speeds by reducing latency and increasing bandwidth. RAID controllers manage groups of drives in configurations that improve speed, redundancy, or both. BIOS or UEFI firmware plays a critical role in detecting storage devices during startup. During post, the firmware scans for connected drives and determines which one should be used to load the operating system. It also enables or disables storage ports, controls boot priority, and may allow users to toggle storage modes such as AHCI or RAID. If the firmware cannot detect a drive, the system may fail to boot or display errors during startup. The performance of a storage controller can significantly impact how fast a system loads applications, opens files, and boots into the operating system. NVMe-based controllers, for example, offer much faster access times than traditional SATA controllers because they communicate over high-speed PCIe lanes and reduce command processing overhead. In systems where speed and responsiveness are critical, such as gaming PCs, editing workstations, or database servers, the type of storage controller can make a noticeable difference in user experience. RAID, which stands for Redundant Array of Independent Disks, is a storage configuration supported by many controllers that combines multiple drives for improved performance, redundancy, or both. RAID 0 splits data across 2 or more drives to increase speed but offers no fault tolerance. RAID 1 mirrors data between drives, creating redundancy in case of failure. More advanced levels like RAID 5 or RAID 10 balance speed and redundancy. While RAID is more common in enterprise systems, some desktops and motherboards support basic RAID configurations through onboard controllers. Troubleshooting GPU issues requires attention to visual symptoms and system logs. Common problems include graphical artifacts, screen flickering, sudden black screens, or performance drops. These issues may stem from overheating, outdated drivers, or failing hardware. First steps include reseating the GPU, checking power connections, and updating drivers. If a system has integrated graphics, switching temporarily to that output can help determine whether the dedicated GPU is at fault. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. BIOS-related problems can also cause major issues. Incorrect BIOS settings may prevent a system from booting, especially if drive priorities are misconfigured or incompatible CPU features are enabled. One common fix is to reset the BIOS to its default settings using a reset jumper or by clearing the CMOS battery. In more advanced cases, a BIOS update may be needed to support new hardware or fix known bugs, but such updates should only be done with caution. Storage controller issues can manifest in a variety of ways, such as drives not being recognized by the operating system, slow read or write speeds, or boot failures. Technicians should check all physical connections first, verify that the drive is visible in BIOS or UEFI, and review controller settings. Testing the drive on a different port or using a known good cable can help isolate the problem. In systems with add-on controller cards, checking for updated firmware or drivers is also essential. All of these components, GPUs, firmware, and storage controllers, interact closely with the operating system. After the BIOS completes post, it hands off control to the OS bootloader. The OS then loads the drivers needed to operate the GPU, configure the display, and manage storage devices. If any driver is missing or misconfigured, the system may crash, display errors, or operate with reduced performance. Ensuring drivers are up to date and compatible with the installed firmware is part of ongoing maintenance. Questions on the ITF Plus exam related to these topics may require you to identify the function of each component or diagnose a scenario involving one of them. You may be asked to match SATA or NVMe interfaces to their performance profiles, identify which firmware interface supports secure boot, or select the correct step when a drive fails to appear in the OS. Scenario-based questions will likely test your ability to connect symptoms with the correct component. In real-world environments, this knowledge is crucial for a range of IT support roles. Help desk technicians may assist users with display issues or missing drives. System builders must ensure compatibility between motherboards, GPUs, and storage interfaces. System administrators may manage RAID arrays, apply BIOS updates, or configure firmware settings for new hardware. Understanding these components speeds up troubleshooting and reduces downtime in any environment. Being able to speak fluently about internal components also improves communication with both users and vendors. If you need to escalate a problem to a hardware manufacturer, clearly describing what you've tested and which part is failing helps accelerate support. Likewise, explaining to a user why their new game won't launch without a discrete GPU builds trust and sets realistic expectations. Technical fluency bridges the gap between hardware details and user needs. In organizations that maintain many systems, firmware and controller management become ongoing responsibilities. Regular firmware audits, BIOS password policies, GPU driver rollouts, and storage redundancy checks are all part of the IT team's workload. Even in small businesses or home labs, knowing how to configure these components is essential for creating stable, secure, and efficient computing environments. The rise of virtualization in cloud computing hasn't reduced the importance of these components. Instead, it shifted where and how they're used. Virtualized environments still rely on powerful GPUs for rendering or VDI acceleration, advanced BIOS settings for virtualization extensions, and high-speed storage controllers for I/O optimization. Whether physical or virtual, systems still depend on these internal components to perform reliably and efficiently. Modern computing increasingly demands performance tuning and component awareness. For example, pairing a fast NVMe drive with a slow SATA controller defeats the purpose of the upgrade. Using a high-end GPU without proper cooling may cause thermal throttling. Enabling UEFI features without understanding bootloader implications may lock users out of their systems. These are avoidable mistakes that a well-trained technician can help prevent through careful planning and documentation. To summarize, graphics cards, BIOS, and UEFI firmware, And storage controllers are core components that define how a system functions beyond basic processing. They determine how visuals are rendered, how devices are initialized, and how data moves through the machine. Their configuration, compatibility, and maintenance directly affect speed, stability, and support requirements. Understanding how they operate and interact equips you to troubleshoot, build, and manage systems confidently, both in the exam room and in the field. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.